So one of the very important things that computers do is shifting bits. And at first, it may not seem very important. It may not be something that you think, oh, this is great that computers can do this, but allows us to do some things that are beneficial. For instance, if we want to multiply by 2, because we're in base 2, we just move everything over to the left one place. Or if we want to divide by 2, we just move it to the right by one place. And so that's kind of cool. But the other thing that we can do is we can take a number, we can take an 8-bit number and break it apart into two 4 bits and then reassemble it and still get that 8-bit number. And this is the way that we encode hexadecimal. So the first thing we should talk about is what is hexadecimal? Hexadecimal is a representation with a base 16. So we're very familiar with base 10. That's the decimal system that we use all the time. And we're familiar with binary because that's what we've been working with primarily with a lot of these exercises is the ones and zeros. But base 16, we don't have numbers for that. We don't have a single number for 11. We don't have a single number for 10. We don't have a single number for 13. And so what we do is in computers, when we get to those, we start using letters. We go 1 to 9, and then for one value that represents 10, we use the letter A. And at first, this seems kind of pointless. Like, why would we do that? Well, it's easier to write. If we have an 8-bit number somewhere in the range of 0 to 255, what we can do is we can take that 8-bit, divide it in half, and then we have two numbers that we can represent in base 16. And if you think about it, one other thing that you hear often is base 32 or base 64 encodings. And we're doing the same thing, is that we're taking we're taking it and breaking it apart in different sets and then representing it in a different base. So for this one, what we have is we have sets of RGB values. And what we need to do is we need to take the 3 values, break them down into their hex value, and then combine them and output them. So let's start. So the first thing that we need to do is load our input string. And so we'll do that with our load register. And we'll put this in R4 because that's the first one that we should generally use. Let's put our registers section up here. And then we're going to think ahead a little bit. So if we have a base 16, how do we actually display the number that we're trying to get to? And if you think about our ASCII or our integer to ASCII implementation, what we did is we used the ASCII of 0 and then just added on to that. And so we can do something similar like that. And so what we need to do is we need to make sure that A comes after 9. However, if you look at the ASCII table, after 9 it comes colon, and then semicolon, and then less than sign, equality sign, greater than sign, question mark, and at sign, and then we get A. And so what we can do is we can kind of give it a new ASCII table in a way. So let's create a part in memory here, and we'll just call it hex string, and it'll be ASCII. And what we're going to do is we're going to recreate our table. So we'll have 1, 2, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we'll just do A, B, C, D, E, F. And in this way, what we're doing is now what we can do is when we're looking for a character, instead of adding it to the ASCII value of 0, we can just say the address of the hex string plus however many numbers it is, and it'll give us the letter. So if we have 0, it's going to be the first address, which is 0. If it's 4, we're going to add 4, 1, 2, 3, 4, and we'll get the 4. If it's 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, we'll get D because it's 13 spaces or 13 memory spaces off from the base. And so let's put this address into memory because we're going to use it fairly often. And we're going to put this in R6. Because we also don't have somewhere to put the result. We can't really write it to the same place as input because it's not similar. For the input, every number is going to be one byte. But when we output it, we have two ASCII characters. So output is going to be twice as large as the input. And so for our output, we could either have 2 times all of them. So 3, 6, 9, 12, 1, 2, 3, 15. So 30, we could do 30 bytes. But we also could do just simply 1 and reuse that space over and over again. And let's do that because it's going to save us a little bit of space. This is a little bit of over-optimizing, I guess, but... and so we need the 6 letters, 1, 2, 3, 4, 5, 6, and then we need the line ending. So we're actually going to need 7 bytes for our output. And so let's load some of this stuff. So in R6, we'll put the hex string. And because we're going to reuse this memory, we don't need to load the outstring address here because we're going to have to reset it for every loop. And so let's load the first number. Let's update our registers before we get too far ahead of ourselves. And for the temp space, let's use R8. And you may think, why R8? Why we skip R7? R7 is what we're going to be using for our write supervisor call. And so if we're going to be writing stuff on every loop, we might as well just keep the write number there. And then we don't have to keep entering it every single time. Or if we're worried it's going to change, then we can just do that. And we can even write it every single time. But we're not going to have to fight between the write calls and make sure that it's not going to change. And so R8 will be the current byte. And so let's load the first number to get all started. So load register byte into R8, the value that is at R4, and increment the address. And that should be all the prep that we need for our loop. So let's make our loop string. An important thing to note at the top is that I made it so that none of the red colors are 0. And in this way, what we have is an null terminated set of data again. In real life, it's very possible that you'll have a 0 as a first value for red, and you would have to change the implementation slightly. But for this, the main focus is on masking and shifting, and you'd be doing that in both instances. So for now, just know that we're going to use a null terminated set of data, but in real life, there's a good chance that you'll have 0 as a red value. So we'll compare this first value in R8 to 0. And if it is, we'll use a branch if equal, and we'll go to our exit routine. We'll just put our exit label down there. Oh. So the first thing that we need to do is, as I said, we're going to be resetting the output string every single time. We're going to reuse it. And so let's take a second here and reset where the address for the output string is. Oh, put that in R5. And we need to do this because the same way that we step through values to store them, R5 is going to change as we loop through these. And then the other thing that we need to do is we need to make sure that we're only taking 3 bytes every single time. Because if we just kept writing, every group of 3 is not null terminated. It's that the whole list is null terminated. And so we need a loop counter as well. And let's put this down at R11. And you may think, this one, why is it R11? When you look at a piece of work, or you listen to a piece of music, or you read a book, or you look at source code, I think that one of the giant misconceptions, and especially being a musician, it's very prominent, is that the thing was created from beginning to end without any revision. That whoever created it got it perfect on the first time and it never changed. And this is absolutely false. It never happens. And so after working on this code multiple times and changing things around, what I ended up doing in R11 is add the loop counter. Um, and so obviously when I'm doing this, I'm not doing it as an absolute live streamcast of like creating these things. It's more of an educational, like planned ahead, like this is how you do it, this is how you figure it out. And so the only reason why it's R11 is because over the revisions that I've done, over the work that I've done, it just so happened that I added the loop counter later, or there were some other things that I added previous that I didn't need, or I did some kind of design change of how to figure this out. And so I'm going to use R11 as the inner loop counter. If you wanted to use R9, that's fine. You would just have to know that everything when I say R9 is not going to be R9 and all the R11s are going to be R9s. Um, but we're just going to use R11 as the inner loop counter. And so what we need to do is reset this counter to 0. And so what this inner loop is going to do is it's actually going to go through the 3 values and write the letters that are associated with the values. And so we'll use the label inner. I know, creative, right? And when this value is 3, we're going to have to get out of it. Because the first time it goes through, it'll be 0. The second time it goes through, it'll be 1. And then the third time it goes through, it'll be 2. So if our counter is 3, what we need to do is get out of here. And we already used our exit label. And so let's use in exit for inner exit. I guess it's maybe a little confusing. Again, you can use branch if equal here. You can also use branch if greater than or equal. But again, in this loop, because we're adding 1 every single time, it should never be greater than. It's up to you. The important thing is that the equal is there. And so here's the actual meat of it. What we need to do is we need to take this number and break it into 2 parts. And so 212, we want to take the upper bytes, or the upper bits first. And this seems counterintuitive. Why would we want to take the upper bits first? If you think about a hex string, the first value on the left is the high bits of the first value. And if we read this of the lower bits first, as what you would think, what would happen is that the first character that we read would be the lower bits, not the higher bits. And so what we need to do is because the first character of the hex string is the higher bits, we need to read the higher bits first and then save that to memory. And so the first thing that we need to do is mask the bits that we need. And we're going to do that with and. And we're going to store this in another register. So it looks like R9 is open. And what we're gonna do is we're gonna take the value that we have read in R8 and mask it against 0xF0. And what this is actually doing is masking the byte by this byte value. So R9. And what this is going to do is it's going to discard everything where there's zeros. The way the AND works is that it has to be 1 in both parts for it to show up as a 1 in the other half. And so if there's any 1 in the least significant bits, the 4 least significant bits, it'll just drop it. And what we're going to get is we're going to get a value in just the top 4 bits. Technically, we don't need to do this. Technically, what we can do is we can just do a right shift, the next thing that we're about to write. But again, sometimes, especially for education stuff, I think it's more important to actually describe how we get the value or what we're doing to look at the value, as opposed to using the quick method to obfuscate it a little bit. And so what we're going to do is we're going to use our logical shift right, and we're going to shift the value in R9 by 4. And what that's going to do is it's going to take the four most significant bits in the byte that we read and set them to the least significant 4 of the register. And what that's going to do is it's going to give us a number between 0 and 15, which is our hex-based objective. And so again, the way that we did it last time is that we added to the ASCII of 0 in order to get our answer. And so we're going to load the byte from memory into R10. And this is kind of magical, I think. So our hex string is at R6. And what we're going to do is we're going to pre-index it before we read it. And so we're going to use this format where we put another number inside the brackets, and we're going to offset it by the value that's in R9. So a couple of things that I'm going to do here. So read and store in R10. Up here, we're going to do R10. And so let's think about this. If we get a number here in register 9, and again, this is what I explained before, if we get a number here in 9 that is 0, then it's going to add 0 to the address and we're going to get 0. If we have a number in here that's 5, we're going to add 5, 1, 2, 3, 4, 5, and we'll get 5. If we're here and we get a number that's 13, it's going to pre-index it by 13. So it's going to be the address plus 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and we're going to get D. And because it pre-indexes it, it doesn't change the address in R6, and we don't have to do anything else. So this will load the correct letter for us all in one little operation. And then all we have to do is store it to the output in the letter that we got in R10, store it to R5, and then we're going to increment it so that we can store the next letter. And so for the second letter, it's almost going to be the exact same. This time, however, the bits that we're looking at are already in the 4 least significant positions. And so when we mask by using and, we'll put this in R9 again because we're done with it. It's actually just going to be 0F. And what it's going to do is it's going to get rid of the 4 most significant bits in this byte and leave us just with the least 4 significant. And so for this one, we don't even need to do a shift here. We just need to do the loading of the letter and the storing of the letter. And this code is going to be the exact same. Oh, not head. Read letter. 5, number 1, and then store an increment. So the next thing that we need to do is we need to increment our counter so that we know we're looking at the second byte in the triplet. And then go back to the beginning of our inner loop. So that'll do that for 3. It'll read the first one, our counter will be 0. It'll read the second one, our counter will be 1. It'll read the third one, our counter will be 2. It'll add 1, and then when we get to the last time, it says our counter is 3, and so we need to go to our inner loop exit, which we were calling in exit. The only thing that we need to do is we need to add a line ending to this. And we can just put this in R10 because that's where we were storing the letters before. And we just need to put in the character of the line ending. And then store that to the output. And we don't need to increment this because it's the last character. And then what we need to do is we need to write it. And since this is always going to be the same length, we don't need to use our null write. We can just give it an actual length. In R7, and remember we didn't use this before because we knew that we're going to use it for the write call. We're going to put 4 because 4 is right. Our first parameter is going to be 1 for standard out. We're going to use our address, our output address for the second parameter in R1. And then our third parameter is the length, which is 7 because it's the 6 letters plus the line ending. And then SVC 0. And then what we need to do is we need to go back to the loop to go again. And when we go back up to the top of the loop, you may think, don't we need to load the next byte? Well, we already did. And so if you look at this, you'll come up here and you'll see that we actually loaded the first byte outside of the loop. So it means we missed something here, because we actually need to load the next byte within the inner loop here. Give me a second. So let's load the next byte here to process. Put it in R8. So a little bit of an oversight here. And so I guess the question is why did I do it this way? And this was one of the things, and I think this is part of the reason why the R11 is in a weird place. Originally, I think when I did this, I had the loading of the first byte within the loop. And that worked fine for the most part, except for it was actually inside the inner loop that we actually moved to the next byte. The outer loop does groups of 3, and so it's not really practical to load the next byte in the outer loop if the inner loop is also going to load the next byte. Then you're going to move it 4 bytes every single time. And so we put the load the next byte within the inner loop here at line 44, and then we don't have to worry about it when we go back to the outside loop. The outside loop in this program is only here to make sure that we have groups of 3. The inside loop is really what does all of the heavy lifting in this. Regardless, after we have the write, it should have written all of the sets of hex here, and so we can just exit the program. We're going to move into R7, the number 1, because 1 is exit. And then the only parameter that we have is the exit code, which is 0. Can't type. And then SVC 0. And that should be everything that we need for this program. So let's try running this. Use our makefile, and we'll run it. And we have a segmentation fault. Let's look at this and see where we did something wrong. So I can't, off the top of my head, find where this is at. So let's use GDB and see if we can figure out where we did this. Let me see our makefile. So our makefile has the G flag on it, which is going to allow us to debug it. So we can go GDB main. And you're not going to be able to see, I think, the whole screen here. What we're going to do is we're going to say break on the start, and we're going to try running it. And let's just step through this and see where it's failing at. And you can see here we have at the top the stack that's truncated, and then we have the actual code that's being ran, the actual byte code, and then the next box is the actual source code. And so let's step through this and see what it's freaking out about. We load it, we store it into R5. We get the second mask. We load it into R10, store it in R5. That looks fine. Here's the second byte. And the third byte. And now what should happen is that we added 1 to the counter. Oh, right there it is. And so I messed up the counter number. So here we're comparing the counter to R11. And down here, if you look at line 45, I mistyped it and made the counter R6. So let's open up our main file again. And in line 45 here, we're going to change this here from 6 to 11. And let's try making it again and running it. And then let's see if we get the correct values. DEE4BC, 96ACB7, 36558F, 40376E, 4820. And so those are the correct values. So we had a little trouble in that one, but we got it to work. And we've successfully converted our bytes to hexadecimal.